Hey, welcome back to graph theory. In the past few videos, we've been discussing adjacency matrices. We've been looking at their properties and ways to calculate their eigenvalues when the graphs are particularly nice. In this video, we're going to focus on some applications of adjacency matrices. We'll look at some examples where we're dealing with a graph that represents flights between cities. Let's quickly review the definition of an adjacency matrix. If we have a graph G of order n, where the vertices are labeled v1, v2 up to vn, we define the adjacency matrix A sub G to be the n by n matrix, where the ij entry is equal to 1 if there is an edge vi vj, and otherwise the ij entry is equal to 0. In the earlier videos, we saw how to calculate eigenvalues for some families of graphs, including complete graphs and complete bipartite graphs. In this video, though, we're going to focus mostly on applications, and we'll see some example problems. And like I said, we're going to focus in particular on graphs where the vertices represent cities and the edges represent flights between cities. Since we're focusing on undirected graphs, we're going to assume that if there's a flight between two cities, there's also going to be a flight in the opposite direction. So before we get to the adjacency matrices, let's look at some questions that we might want to ask about a flight graph. First, if we have two cities in this graph, X and Y, is there any way to fly between city X and city Y? Another question. If there is a way to fly between city X and city Y, what is the fewest number of connections to fly between those cities? For some given integer k, how many ways are there to fly between city X and city Y that have k connections? And if we look at the whole graph with all of the cities, is the graph connected by flights, or are there multiple connected components in the graph? And we can use the adjacency matrix to answer all of these questions for any given flight graph. So we'll let A be the adjacency matrix of our given graph G. And first, let's focus on the matrix A squared, the square of A. Let's look at the ij entry. When we calculate the ij entry of A squared, when we multiply A times A, the ij entry is just going to be the number of k for which there is an edge vi vk and there's an edge vj vk. This quantity is the exact same quantity as the number of walks of length 2 from vi to vj. Now we can proceed by induction. So we can suppose that the ij entry of a to the r is the number of walks from vi to vj of length r, and this is true for some r greater than or equal to 2. Now we're going to look at the ij entry of a to the r plus 1, which is the same thing as a to the r times a. So that means that the ij entry of a to the r plus 1 is just going to be the sum over all k for which vj vk is an edge of the number of walks of length r from vi to vk. Now this quantity is the exact same quantity as the number of walks of length r plus 1 from vi to vj. So that completed our induction, and we just showed that the ij entry of a to the k is the number of walks of length k from vi to vj. Now, if we want to calculate the number of walks of length k from vi to vj, we see that this is easily calculated from a to the k. But calculating a to the k itself, this might take a lot of time unless we do it in an efficient way. We can recall that A is symmetric. And we know some facts about symmetric matrices. One of them we mentioned in an earlier video. Symmetric real matrices have real eigenvalues. That tells us that adjacency matrices must have real eigenvalues. More than that, though, symmetric real matrices are diagonalizable. So this tells us that so are adjacency matrices. So that means that our adjacency matrix A, we can write as A equals P times D times P inverse, where D is a diagonal matrix. And that gives us an easy way to calculate A to the K. We can just calculate it as P times D to the K times P inverse. And raising D to the K is much simpler than raising A to the K, because all we have to do is square the entries on the diagonal. So this already gives us a way to answer one of the questions. That question being, how many flights between city X and city Y have exactly k-1 connections? Another way we can ask that exact same question is, how many flights between city X and city Y have exactly k legs? So first thing, we can calculate the adjacency matrix of the given flight graph, and that's our matrix A. Then we want to diagonalize that matrix. So we calculate its eigenvalues. The eigenvalues give us the diagonal matrix D, and then we calculate the eigenvectors. The eigenvectors give us the matrices P and P inverse. Then we want to calculate A to the K, so we can just calculate P times D to the K times P inverse. And if city X is represented in the graph by the vertex VI, and city Y is represented by the vertex VJ, then we can just look at the ij entry of the A to the K that we just calculated. That ij entry will give us the number of walks of length K in our flight graph between the vertices VI and VJ. And walks of length K corresponds to flights with K legs, which is the same as flights with k-1 connections. There were also some other questions about flights that we were curious about. So one of the questions, is there any way to fly between city X and city Y? We'll also assume that there's at least two cities for these questions, since otherwise none of these questions would be interesting. So this first question, is there any way to fly between city X and city Y? All we have to do to answer this question is we'll just look at powers of the adjacency matrix, starting with the adjacency matrix itself, and then squaring it and cubing it, and so on and so forth. We'll assume that city X is the vertex VI, and city Y is the vertex VJ. And we'll calculate these powers of the adjacency matrix, A to the R, for R equals 1, 2, up to n. And we'll only halt if we find some R such that the ij entry of A to the R is non-zero. And if we find for all R from 1 up to n that the ij entry of A to the R is 0, then that tells us that there's no way to fly between city X and city Y. If there was some way to fly between city X and city Y, then there would be some walk in our graph between the vertices VI and VJ of length at most n, because there's n vertices in the graph. So we only have to check up to n. Here's another question that we were interested to know. What is the fewest number of connections if we want to fly between city X and city Y? This question is closely related to the last one, and we can use the exact same method to answer it. So we just calculate powers of the adjacency matrix, starting from 1 and going up to n, or until we hit some r, for which the ij entry of a to the r is non-zero. The first r, for which the ij entry of a to the r is non-zero, gives us the minimum number of legs if we want to fly from city X to city Y. And we can subtract 1 from that to get r minus 1, and that would give us the minimum number of connections if we want to fly from city X to city Y. And then there was another question. So the last question was about the whole graph. This is about whether or not the graph is connected by the flights. To answer this one, we can combine all of the powers of the adjacency matrix. So we can look at the sum, a plus a squared plus a cubed, all the way up to plus a to the n. Now, we're going to require, for the graph to be connected, that all of the entries in this sum be non-zero. If there's any entry, ij, in this sum that's equal to 0, that means that there's no walk in the flight graph between vi and vj of length at most n. And that would mean that our flight graph would be disconnected. Also, if there's some entry on the diagonal that's 0, we assume that our graph has at least 2 cities, so n is greater than or equal to 2. So having an entry on the diagonal equal to 0 would mean that at least one of the vertices is a singleton. Assuming that the ii entry on the diagonal is 0, it would mean that vertex vi is a singleton. So that would also make our graph disconnected. And if we find that all of the entries in this sum of matrices, powers of the adjacency matrix, if all of the entries are non-zero, then that tells us that between every pair of vertices in our graph, there's some walk of length at most n. So that's another way to say that our graph's connected. So this sum gives us all the information we want about whether or not the graph is connected. And we can say that succinctly by just stating that the graph is connected if and only if there are no zeros in the matrix equal to that sum. So we can apply what we just discussed to a nice small graph. This graph only has 6 vertices, A, B, C, D, and E, and F. We can think of them as cities. And so a natural question we can ask is how many walks are there from D to E of length 3? If we want to answer this, we could just examine the graph, or we can calculate it with the adjacency matrix. So let's first examine it and then see if we get the right answer by checking with the adjacency matrix. So we want walks of length 3 from D to E. So one of them is D, A, B, E. One of them is D, C, B, E. And one of them is D, C, F, E. That gave us 3. And it looks like there's no others. So now let's check it with the adjacency matrix. Based on the graph, we can write down an adjacency matrix, and there it is. That's our matrix A. If we want to know the number of walks from D to E of length 3, we'll just raise A to the 3rd power, and we'll look at the 4, 5 entry because we're looking at walks from D to E. The 4, 5 entry, this is 3. So the adjacency matrix told us that there are 3 walks of length 3 from D to E. And that agrees with what we saw with our eyes. And here's a question for you. How many walks are there from A to E of length at most 3? We can look back at that graph. So there's our graph. A and E are there. We want to know how many walks are there of length at most 3 between A and E. And that brings us to the end of this video. Thanks very much for watching.